Howdy everybody, welcome back to Lab Hours. Today's mini lecture is going to be on regression. And fun fact, if you're taking Econ 378 under the current curriculum as of the date of this posting, you're actually on the final mini lecture or the final topic that we're going to cover before the first midterm. So congrats for making it through the first part of the course, and hopefully you've been enjoying it. If you're just doing it by yourself, you've also reached a milestone. That's what the milestone is, so congrats. The Tommy Triple for today, linear regressions. We're going to talk about the model, the idea of what is the purpose of a regression, like what is it, and like what is the formula and stuff like that. We're going to talk about the slope and intercept terms that come from that model. I have these two different notations here that I will be using throughout the video. This is read as beta 1, not like beta sub 1 or B1 or anything like that. So this is beta 1, Greek beta, right? Beta 1, beta naught, okay? Most places in econ, you'll see use beta naught, beta 1. A lot of times, I think in the stats world, you'll see A and B instead. These are both just representative of slope and intercept terms, and I will explain what those are in just a minute. I just want to make you aware as a heads up of these notations being equivalent so that if I forget one or something like that, you can go and fill in the blanks in the video, okay? If you saw like A and B on a test or on an assignment, but you only learned it with beta naught or beta 1, this is hopefully going to make that connection easy for you. So let's jump right into the model, and as always, we're going to give you the math and then the intuition. The interesting thing about models in econ in general is that models are kind of theory and intuition by themselves, so I'm just going to write it out for you, and then we'll talk about it, because this is a pretty interesting one. The idea, really quick, we need to talk about is what the word regression means and where it comes from. So I'm going to start with a little bit of an unrelated example, and then we're going to connect it, okay? If you were to roll 2 dice, what are the possible outcomes, right? If I roll 2 dice, right, what can I get? I can get anywhere from 2 to 12. And what if I wanted to know what is the relationship between rolling 2 dice, I take 2 dice, I roll them at the same time, like what's the average roll of 2 dice? And let's say you didn't know what it was. Like, we know it's 7, right? Maybe those of us who've played dice games or whose dads took their honeymoons to Vegas, right? We know that the average is 7, right? But it's not always that easy. So maybe what you'd want to do is conduct an experiment, and you'd want to take down some data. You'd just roll the dice a bunch of times. So let's roll the dice a bunch of times, and let's just see what we could predict as the average. So the first dice roll, maybe you get a 4. And then the second dice roll, you get a 2. Crazy snake eyes. And then the third dice roll, you get a 9. And then the fourth dice roll, you get a 5. Something like that. What's your average? What's your best guess at the average at this point? Well, it's going to be 4 plus 2 plus 9 plus 5 divided by 4 because you've rolled the dice 4 times. And what that's going to give you is 6 plus 9 is 15. That's going to give you 20. 20 divided by 4. Your best guess for the average of 2 dice when you roll them at the same time is going to be 5. 4 plus 2 plus 9 plus 5 divided by 4, that's just 5. And if you were to say, well, I've rolled these dice 4 times, and my average roll was 5, so my best guess as to the average at this point is kind of 5, right? Now, we've learned previously that, like, law of large numbers and stuff, I actually don't remember if we've done that yet, but there's this idea that if you were to keep doing this over and over and over again, across the possible ranges of 2 and 12, you would see fairly few 2s, because there's only one way you can get it. You have to roll a 1 and a 1, right? And then you would see slightly more 3s, right? Because you could roll a 1, 2, or you could roll a 2, 1, right? And so you keep going on and on like that, and then you realize, oh, I'm actually seeing a lot more 7s than I am 2s and 12s. Because, you know, you can get a 7 with any combination of your first dice roll and a specific output from the second one, right? A 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5, and so on and so forth, right? So you'll find out as you do this on and on over and over again, you're actually hitting 7 most of the time. And not only that, not only are you going to hit 7 more often than your other rolls if you keep on doing this over and over and over again, but you'll also find that if you add up all these dice rolls and then divide by the number of dice rolls, your number is going to get closer and closer and closer to 7 as you continue. And if you don't believe me, we'll talk about this later. This is called the law of large numbers. It says that sample means converge to true means, as the number of observations approaches infinity. We'll cover that later. But the whole idea is that we want to capture the average relationship between some variable y and some variable x, right? We want to know how x affects y on average, right? So the model looks like this. Y is equal to, in fact, let me not erase this dice example, right? Let's just make it smaller and put it up in the corner. Because this is an important idea to keep in mind. What is regression, right? As you keep rolling and rolling these two dice, your sample average that was 5 when you started, right? When you did your first 4 rolls, it was 5. But as you've done your 4,000th roll, that number 5 is going to move around, and then eventually it's going to stop moving so much, and it's going to converge or return or regress to 7, right? That's the idea. We're going to converge on the true mean. And so we want to converge on the true mean relationship between y and x. This is what the model looks like. Y is equal to beta 1, no, beta naught plus beta 1 x plus some error term. Or if we're using the AB notation, y is equal to a plus bx plus e. These are models. This is our guess as to what the hypothetical perfect relationship between x and y looks like, right? And so we're going to get beta 1 and beta naught from our data. This e, or this epsilon, or I mean it's Greek, it's epsilon, right? This is going to represent an error term individual to each piece of data. Let's take this math that I've given you now and let's combine it with this intuition. We want to find a true mean relationship, or the true average relationship between a change in x and y. If I change x, if I add one more unit of x, what does that do to y? What can I expect to happen, right? So let's check it out, right? Let's say, for example, you're at a party and we have, you want to find out what the relationship is between like number of pieces of pie that someone eats at a party and how they rate that party on a scale of 1 to 10, right? So pie scale over here. And we're not talking about weight, which I think is funny, right? Let's say you have a friend who didn't eat any pie, you have another friend who ate 1, you have another friend who also ate 1, and then you have a couple crazy friends who ate a bunch of pie, right? And then let's say on a scale that they enjoyed the party, right? Maybe this first friend liked the party at an 8, this next one liked it at a 7, the next one liked it at like a 10, the 2 pie person had a 9, and the 4 had like a 2, right? They actually got a stomach ache and threw up and passed out or something like that, right? Let's graph it, right? And as I'm graphing it, I'm going to show you this idea of regression. I'm going to try to model this intuitively, right? So our scale of x, 1, 2, 3, 4, 1, 2, 3, 4. And our scale of y, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So the first person had 0 pie and enjoyed at an 8. 1, 2, 3, 4, 5, 6, 7, 8. This is where they were. That's that first observation. The second observation, had 1 slice of pie and enjoyed it a 7, right? That's probably closer to where 7 is. The next person had 1 piece of pie but enjoyed it at a 10. Then the next person had 2 pieces of pie and enjoyed it at a 9. And then the next person had 4 pieces of pie and enjoyed it at a 2, right? So the question is, how do you draw the best line that describes this data? Like on average, would it look like this? Would it maybe look like this? Would it look like that? Who knows, right? But let's go back and try drawing the data again a different way. Let's do it one by one and try to fit a line, right? Let's just do these first 2 pieces of data like we have here. What does this line look like? What is this relationship? Well, this says, and actually this is this line right here, this 7 line right here is actually the one that we're talking about, right? These 2 pieces of data, these first 2 pieces of data suggest that the relationship between number of pieces of pie that you've eaten and enjoyment of the party looks exactly like this. Adding one additional, this model would suggest, or this line from these two pieces of data would suggest that adding one additional piece of pie to your stomach decreases your enjoyment of the party by 1 point, right? That's really easy to see with just these two observations. There's only really one line you can draw. The trouble is, what happens if we throw in this next friend who enjoyed it at a 10 and had a piece of pie? What does that look like? Well, now we've gone and thrown a whole loop in the system. There's so many different lines that we could draw to try to describe something like this, right? What happens if you don't eat any pie? I mean, you're still sitting at an 8, but now the question is like, well, what's the actual relationship between eating pie and stuff? Well, if you were to go by average relationship, you would say, well, on average, it looks something like this, right? Because the intercept is the same. You still, our only person who didn't eat any pie liked the party at an 8, right? And then if we just like average between how far away these two people are, we get something like adding an additional slice of pie. I mean, it made this guy worse by 1, but it made this person better by 2, so it must on average like increase by like a half or something like that, like we're averaging something, right? Who knows? But then add in the next piece of data, this 2 and 9, and now all of a sudden we have a 2, 9, right? That's more evidence for this purple line, honestly. It's looking really good, right? Add 2 slices of pie and you go up to a 9. And we just have this guy right here that is bringing everybody down. And in fact, let's keep that on the purple line because it fits it really well, right? Now add this last piece of data. Somebody ate 4 pieces of pie and enjoyed the party at a 2. And that's crazy, right? Because now all of a sudden it looks like we're back on this blue line. But it doesn't, because now we have to factor in these two guys. So this line actually probably looks more like this or something, right? Something like that. Hopefully you can tell that as we continue adding more and more people to this pie and scale data set, this line will keep jumping around, but eventually as we get enough people, it's going to come down to some true line that will represent the relationship of adding another slice of pie and like how much you enjoyed the party, right? And maybe we'll add another person with 0, so now we have to change the intercept, right? And maybe it looks like this, and we have to go up and down and up and down and up and down and up and down until finally, with enough observations, we can say this is what we're pretty sure the relationship looks like. So we have finally regressed the average relation between eating slices of pie and enjoying a party to what we believe is the true enjoyment factor, right? This is the idea, just like these dice. As you keep doing it, you're going to get closer and closer to what is actually true as you shift stuff around. That is all of the intuition. We've just spent 13 minutes talking about the intuition behind this model of how you can predict a change in y using x, or regress y on x. Those are the words that we use, right? We try to predict y using x. We're trying to predict your party enjoyment using how many slices of pie you ate, right? So what we say is we regress y on x. But I haven't given you any of how we actually figure that out yet. This has just been pure intuition and modeling for almost 15 minutes now. So let's get into the math. And now that we've done all this intuition, the nice thing is, like, I'm about to explain to you slope and intercept intuitively. Or with the math, right? Slope and intercept, I've just given you that intuition here. The slope of this line is going to be beta 1. The intercept is going to be beta naught. And hopefully you can see if I added in another 0, like 4, this beta naught would turn into like 6, right? If this were a data point, we'd have to average it, right? And start from here and then go like that, right? That's all the intuition. The rest of the thing can just be math, and this can be a short review. So, did we check off model? We did. Let's talk about the slope. Beta 1, or B, as some people like to call it, is equal to, there's 2 different formulas, they're equivalent, and I'm going to show you how to get from one to the other. The first one looks like this. Correlation of x and y, and remember, this is just for when you have one x and one y. You'll deal with all the multivariable cases later, in like later classes, Intro to Econometrics, Econ 388 if you're at BYU, later classes if you're not, right? Rho, the correlation coefficient that we learned about in the last mini lecture, right? That was the last mini lecture? Or a couple mini lectures back, right? Because last time we did conditionals. You know how to find rho. You know the formula for rho. Beta 1, or B, or the slope coefficient, is rho times standard deviation of y over standard deviation of x. This is basically how are the things related, and then standardize it to this idea that we want to predict y using x, right? Not too much intuition, and actually it's mathematical, the reason that we're doing this. All of this, the whole idea is that we want to minimize this distance right here for all the points from the lines. We want to minimize the vertical y distance between each point and any line we draw. So like the purple line looked like this. That's about as small as you can get these distances, right? In absolute terms, right? Because the negatives, we don't want to cancel out the positives, right? That's what these e's are, by the way, is just the distance between each of these points vertically from the lines that we draw. And you can see, for example, that this line would have a huge error term to the purple, but it has a 0 error term to this blue line and a smaller error term to this red line, right? So these e's are going to be determined by how we pick beta naught and beta 1, and we pick beta naught and beta 1 expressly to make these e's as small as possible after we account for the fact that some of them can be negative, right? We do that by squaring them. So the whole way that we've picked this exact formula right here, is by minimizing the sum of squared errors, right? Epsilon squared I, right? Sum from I equals 1 to however many observations that you have, right? We want to take all of these distances, square them so that negatives don't matter, and then add them up and make that as small as possible when we're fitting this line, right? That's how we get this formula right here. Now, you'll remember from the lecture where we talked about the correlation coefficient that the formula for the correlation coefficient is covariance of x and y over standard deviation of y, standard deviation of x. And so in this formula, we're multiplying that by standard deviation of y over standard deviation of x. And that gives us the second equivalent formula that can be helpful for like story problems in textbooks or stuff like that, where they only give you certain pieces of data. And that is covariance of x and y over the variance of x, or standard deviation of x squared. Hopefully this isn't too tough to see, right? These two are the formulas that, if you can remember them, you'll always, at least in this class, be able to calculate, even just from like a table of data. You already know how to calculate correlation. You know how to calculate these standard deviations. You know how to calculate covariance. You know how to calculate variance. Just pick whichever one is easier for the problem that you're working on. These formulas are equivalent, and just use them, right? Not too much more to say intuition-wise. Just learn these formulas and how to calculate them. And the nice thing is, if you just know this formula and you remember how to do these individual parts, because we've already learned them, you're good to go. Just remember the formula. And remember, why is y on top? Because we're trying to predict y with x, right? Predict y using x. You might get a problem that asks you to predict weight using someone's height. And then in the second part of the problem, they might ask you to predict someone's height using their weight. Which one is y, which one is x? Well, whichever one you're trying to predict using the other one is the y. And the thing you're trying to use to predict the other one is the x. If I'm predicting weight with height, I'm using height to predict weight. That means that I'm predicting y with x, so I'm predicting weight with height, or I'm regressing weight on height. That's how the terminology goes. That's everything we need for slope. And you might be wondering, Tommy, why did we not start with the intercept? It looks like it's a lot more simple. Well, the trouble is the formula for the intercept uses the slope beta 1 or b, right? This is not going to be too tough. Beta naught is equal to a, right, in some notations, which is equal to y bar, or the average of y, or mean of y. Sometimes we would call this, right, like mu of y, because we've been using mu for mean in the previous lectures, right? Mu of y minus beta 1 mu of x. The whole idea here is you're taking the average y and subtracting the average effect of the average x, because this beta 1 here is the average effect, right? This slope, you can see, because we're minimizing all of these, it turns into like the average effect of an x, right? So this beta naught is just covering all of the averages. And what it does is it reflects the fact that, if x has no effect, then you can just predict as the average of y, and then you're basically back to dice roll territory at this point. If x has no effect and this beta 1 is 0, then your best guess at predicting y is just going to be, what's your average y, which is pretty cool. But over here, right, beta naught is equal to, what would happen if x was 0? Well, it's 8. We put it at 8. Like, that was the intercept right there, right? But if it were different, right, like if the average y were 4, we'd just go in and calculate everything. It'd be slightly different, of course. But, like, there's really no more intuition here. This is a linear model. It's just y equals mx plus b from, like, 6th or 7th grade algebra, right? This is the slope. This is the intercept. This is the intercept. This is the slope. That's pretty much everything you need to know about regression for this test. Well, for the test, but also for this class, which is nice. Just this idea of, like, we can get an idea of the average relationship between two things, and we can maybe use that to predict stuff. We can plug in a number for x and get a y that pops out because we just assume that this turns into 0. We use expected values and stuff to do that, and it's the cool thing, right? Especially because we, pick this e to try to, we try to minimize this and go away. It just so happens to make the x's uncorrelated with the e so that you can, like, only have random variation. It's a whole thing. Talk about it later. This is all you really need for this class. And so that's actually going to cover everything from this mini lecture. Just we talked about the idea of what is a regression, like why do we call it regression? It's because we're regressing to a mean relationship. And we talked about the underlying fundamental model that we try to present in order to make this true, right? That we think is true between x and y. So when we, regress y on x or predict y using x, those are ways that I remember and know how to keep which one is y and which one is x, right? So, and then we just talked about the formulas for slope and intercept. Pretty easy, pretty straightforward in terms of, like, these two steps, because it was just math formulas. All of the intuition hard work was in the model. And don't worry, if you don't get it perfectly right now, we will talk about it again later, and you will talk about it again later in the major, especially when you take 388. That one is going to be a really good class, and I recommend it. As always, if you have any questions, feel free to leave a comment, or if you're in the class, email me at tmorg.ta@gmail.com, and if you're not in the class, email me at labhours@tmorg.org. As always, if you want to subscribe, you'll be able to see them come out, leave the video a like if it was helpful. You know how it goes. It's YouTube. What can you do, right? But again, questions, I'll respond to comments, I'll respond to emails, no matter what. And hopefully this was helpful to you. Next time on, I don't even know what we're going to do next time. I got to scroll through really quick. Lab hours, by the way, if you're taking the class, the next things that we'll talk about are, like, the basics of using Excel and Stata, which are two, like, statistical, well, Excel is like a spreadsheet software that most people are familiar with. Stata is like a statistical package that we use to make handling huge amounts of data, like, more convenient. So that's what the next, like, lectures will be on. I won't be doing mini lectures here in lab hours for that, because I will actually on the channel have my 2 versions of those full lectures uploaded as, like, example lectures. So you'll be able to go to those basically whenever you'd like, as, like, the full lectures, not just as a mini. The next mini lecture will be on continuous distribution. So we'll be taking these probability distributions that we've been dealing with in the past 2 mini lectures, and we'll be moving, instead of, like, it can only take on values 0, 1, 2, 3, 4, 5, to, like, the range 0 to 1 and every number in between and stuff like that. So that'll be a fun one. Droned on a little bit long, but of course, as always, questions. If you're in the class, tmorg.ta@gmail.com. If you're not in the class, labhours@tmorg.org. Thank you so much for watching. Hopefully we'll see you next time. Have a wonderful day. Bye-bye.